Today we live in a quite complicated time which creates for us a lot of problems to solve. Among them, I guess the importance of energy conservation and medicine is very hard to overestimate. If you could imagine just for a second a world where solar cells can absorb every color of sunlight, or ultra-sensitive bioimaging systems which can provide you a deep, real-time insight into the processes in human body, then you will see a bit better world than we have right now. And one of the promising tools which can help us to make a step towards this world is the upconversion. The idea of upconversion is very simple: to transform the frequency of electromagnetic light from low to high value. And it is possible with some small tiny particles, upconverting particles. This process is well known and deeply studied, but unfortunately it has one huge drawback. The efficiency of the upconversion is very low. And today I would like to tell you about some promising strategy which could significantly enhance the efficiency of the upconversion. It is related with plasmonics. So the combination of upconverting particle and plasmonic particle paves a way to a wide variety of different physical and chemical phenomena with one single name: Plasmon enhanced upconversion. And here at the University of Illinois, we try to deeply understand these phenomena and conduct some novel experimental and theoretical research. So I would like to start my presentation by providing you some background information. Then I'll move on to some simple example of single plasmonic particle and single upconversion particle interaction. After that, I will expand this example by collection of plasmonically enhanced upconverting particles. And finally, I'll give you some conclusive remarks. So let us start with some basics of upconversion. Actually, the upconversion is a two-photon process which involves intermediate long-living state. To put it simply, the upconversion can be described as follows. Every particle has at least one electron in the ground state. Assume that the upconversion particle absorbs light at some certain frequency. Then this photon will excite the electron so it goes up to the intermediate excited state. Here at the level 1, this electron will wait to another photon to be absorbed, and if it happens, then the electron goes up to the highest excited state. After that, the electron will inevitably goes back to the ground level, and it will release the photon with higher frequency. This is the upconversion. So you put photons with low frequency to your upconverting particle, and you get the photons with higher frequency. Here I need to make one remark. Unfortunately, the electron cannot live infinitely long at the intermediate excited state. So the second photon should strike the electron before it goes back to the ground level. The problem here is that the probability of such complicated events is very slow. It means that the efficiency of the upconversion will be small as well. For example, if you put 1000 photons to the upconversion particle, then you will get only one upconverting photons out. And this is a very big problem. because if you want to effectively utilize this upconversion process in some useful application, you will probably need huge amounts of upconverting particles. So there is a necessity to enhance somehow this process. And luckily, there is a very effective and convenient way to do it. Let's move on and get know it. Tiny metal particles, plasmonic particles, have some very special feature. At some certain frequency, they can significantly enhance electromagnetic fields and create very unique local surrounding, which in turn can enhance the upconversion process. This is the basic idea of Plasmon enhanced upconversion. Today, experimentalists can synthesize wide variety of plasmonic particles with different shapes, materials, sizes, and so on. And if you vary these parameters, you can adjust the frequency of the plasmonic particle. So, if you take the plasmonic particle with the resonance frequency omega-1 and put the upconverting particle, which absorbs light at the exactly same frequency, you will have some hybrid system. And in this system, the plasmonic particle plays the role of an amplifier. It collects huge amounts of incoming photons and redirect them straight forward to the upconverting particle. So you have the increased amount of incoming photons, and of course you will automatically get the increased amounts of outgoing photons. This strategy is called as excitation enhancement. Of course, you can choose another one plasmonic particle with resonance which is matched to emission of your upconverting particle. In this case, the upconverting particle will excite resonance in plasmonic particle, and then plasmonic particle will release additional photons at the upconverting frequency. So this is the emission enhancement. Okay, we have learned the basic idea of Plasmon enhanced upconversion and considered two distinct types of these enhancements: the excitation enhancement and the emission enhancement. And now we are ready to move on to our research field, which deals with collections of particles. In real life, you are not supposed to have single plasmonic particle and single upconverting particle. Instead of this, you will have some solution of these particles. Under solution, I understand the collection of particles floating in some liquid environment, for example, water. And the question that arises here is how to predict the outgoing upconverted signal for a given pump, for a given incoming light, and for a given set of parameters. And this question is very important because there are so many parameters that you can vary here. Size of particles, concentration of particles, materials of particles, intensity of incoming light, and so on. What we are trying to do is to incorporate all of these parameters and take into account all possible phenomena to predict the outgoing signal and to provide some guidelines to get the maximum gain in upconversion. What we already have figured out is that for example, extinction of light plays a significant role in such systems, because the incoming light, the intensity of incoming light slowly decreases while the pump propagates through the solution of particles. So the particles on the left boundary will get more photons compared to the particles on the right boundary. Another example, if we recall to the basics of upconversion and remember that there is some undesirable transition of the electron from the intermediate to the ground level, it will become obvious that the useless photon which has been released during this process can become useful because it can be recycled by neighboring particles. Nobody pays attention to these details, and that's why existing theories fail to predict actual upconverting signal which we see in experiments. I just have provided you few examples of very special phenomena in collection of plasmonically enhanced upconversion particles. And we strongly believe that there are so many more of them which we could reveal and describe by our theoretical approach. I think that what we really need to understand the physics of plasmon enhanced upconversion, because at the end of the day, this process, this tool can be utilized in almost every field area of our life, especially in solar cells or bioimaging. So let me conclude. Today we have learned basic idea of upconversion, which relates with transformation of light from low to high frequency. I have provided you some strategy how can we enhance the upconversion process using plasmonic particles. And finally, we discovered some very special phenomena which take place in collections of plasmonically enhanced upconverting particles. Thank you.